Here we are at example 15 from the 0.2 number 2 set of notes. We're asked to graph this rational function. And right away we notice that we have an x cubed on top and a quadratic on the bottom. And again, just like normal, typically we try and start out by factoring things. So we're going to go ahead and try that out. The biggest thing that we can pull out on top is actually just an x. So they all share that common value of x. And then we would be left with x squared minus x minus 6. On the bottom, we have the difference of two squares, so that's just x plus 3 times x minus 3. Now the top actually can be factored a little bit more. So we end up with x times x minus 3 times x plus 2 all over x plus 3 times x minus 3. And this is now our new function. F of x is the same thing as saying y, so I'm just going to replace it with y. Now, at this point, we can kind of see these x minus 3's. One's on top, one's on the bottom, so they actually end up dropping and canceling out. Now, that's really important because when we start talking about wholes and VAs, certain ones are wholes and certain ones are VAs. To find out our VA, we still set our bottom not equal to 0. So for VA, we have that bottom not equal to 0. Now the only one that we're going to determine for the VA is actually the one that didn't cancel. So this x plus 3 is not equal to 0. If it ended up canceling, it actually now becomes our whole. So then just solving this, we end up by subtracting this 3 from both sides, giving us x is not equal to negative 3. We should see the VA occurring right there. Now for our whole, the one that did cancel, we still solve things the exact same way as the VA, only it's going to be a whole. So we have x minus 3 is not equal to 0, even though it canceled like that. We still have to find out where is that whole at. Adding 3 to both sides, we just see that x is not equal to positive 3. Well, that's all great and wonderful, but we only have the x value, and for a whole, we actually also need the y. Now, what we end up doing is we take our value 3, that x value, and plug it in to our simplified version, anywhere that there's that x. So to do that, we have y is equal to 3 times 3 plus 2 all over 3 plus 3. And now this is going to give us our corresponding y value. So then we end up with 3 plus 2 is 5, times 3 is 15 on top, over 6. So ultimately that y value will come out to be 5 halves, or 2.5. So now we actually have our whole, which is a point at 3, 2 1/2. So we found our VA, we found our whole. Let's go ahead now and move toward finding our horizontal asymptote. Well, for our horizontal asymptote, we have that scenario where we have a degree that's higher on top than it is the bottom, and as a result, we won't have a horizontal asymptote. Now, moving gears towards finding the slant asymptote, what we have to do is take our simplified version that we have and go ahead and, which actually we'll go ahead and just rewrite that for now. So we have y is equal to x times that x, I think it was minus 2 plus 2, all over x plus 3. In fact, even before, let's do more of like the discovery version. Let's go ahead and just graph and see what this looks like. So I'm going to go over to my calculator, clear this one out. And our original function read x cubed. So we have, in parentheses, the top one, x cubed. So caret 3. Let's get off of that exponent by hitting the right arrow. Minus x squared, so minus x squared minus 6x, close parentheses, divided by, now our bottom one in parentheses. So we have that x squared minus 9, close parentheses. Now going ahead and graphing this, we see an image that looks something like this. Now we do have that vertical asymptote happening at -3. So there is that, and that what it appears to be is that there is a slant asymptote happening something around here, but we can't quite see what it is. Now how do we actually find the slant asymptote? Well, from our original graph, because this x minus 3 ended up canceling, that actually becomes, again, the whole. However, we can still find the slant asymptote from our simplified version. Now, how we go about doing that is by distributing in, so kind of actually just like reverse factoring. Obviously, distributing is reverse factoring, but we have to have it back into that quadratic form such that we're used to then using that synthetic division or long division. So we end up with x times x is x squared plus 2x. And this is still all over x plus 3. Now we can go ahead and apply our, in this case we lucked out and we can use synthetic division. So we're going to go ahead and take the opposite sign of this value. So it's -3, throw him in the box, take our coefficients on top, come out to be 1, 2, and 0. Again, can't forget that there is in fact a plus 0 constant at the end, leaving ourselves some space for a bar. And now we just perform our synthetic division. The first one we just drop down. We multiply what's in our box with what's underneath that bar. So -3 times +1 gives us -3, and we're going to go ahead and place that right under the next number in the column. We always add going down. So 2 plus -3 comes out to be -1, and then you just repeat the same process. So -3 times what's under our bar, -1, gives us +3. We place that right underneath the next number. Always adding, going down. So 0 plus 3 gives us 3, and there is our synthetic division. Now again, since we had something be a quadratic, we divided it by a power of 1. We should now end up with something that is a power of 1. So we have x to the 1 minus 1 remainder 3. But again, with synthetic division, or long division, we don't really care too much about the remainder, so we're going to omit him. And as a result, our slant asymptote just comes out to be y is equal to our result of the long division, or synthetic division. So we have 1x minus 1. So when we graph that, you can actually see that if we have a y-intercept of -1 and a slope of 1, it kind of does follow that slant asymptote, at least the graph does. Let's go ahead though and graph everything that we have on our own graph. So we have our vertical asymptote at -3. We have our whole at 3, 2 1/2. And then we also have that slant asymptote at the y-intercept being -1 and that slope of 1. So up 1 over 1. Now we can go, oh, and there's also no horizontal asymptotes, but we don't have to worry about him. Going ahead now and creating our table of values. So if we have an x, make this in purple, x and y. If we went ahead and plugged in, for example, -6, -5, and -4, For negative 6, we would end up with the value negative 8. For negative 5, we ended up with negative 7 1/2. And negative 4, we would get negative 8. So just going ahead and graphing those. For negative 6, we have negative 8. For negative 5, we have negative 7 1/2. And for negative 4, we have negative 8 again. So what's happening is it's going up, it's hugging these asymptotes, it's going up, and then it's going to hug also then our vertical asymptote. Over here on the right side of our VA, instead of actually showing a table, I'd like to actually show the graphing calculator table. So all we have to do is we have our image. Let's go ahead and hit second table. And we see some of those values. Notice at negative 2 we have that y value 0, and at 0 we also have 0. Oops. So at negative 2 we have 0, at 0 we have 0. And again, we can algebraically find those as well. All you would do is just set this top piece this top piece equal to 0 to find that. And so connecting these 3 points, and yes, I said points, because that hole is kind of considered to be a point. And so we should see an image that looks something like that. And in fact, we did from our graph. Really quickly, what I would like to go over is I'm going to maximize this. If I go ahead and take that slant asymptote, let's go ahead and create a second equation where we can actually see this slant asymptote. Well, we know that it's the function y is equal to x minus 1. So this red line is going to represent x minus 1. And then if we just go ahead and graph, we see that slant asymptote and the function is in fact hugging it. All right. So again, I think that's a really nice visual to kind of just see that this is hugging it all the way, even over here especially. So again, that is example 15 from the 0.2 number 2 set of notes.